Wilhelm Stannat, Darmstadt, is speaking about the Stochastic Navier-Stokes-Coriolis equation.
Okay, so I will present some results on Navier-Stokes equation with Coriolis force, which describes the motion of a rotating fluid. The reason will be because, well, I will mention this in the next slides. There is, in some sense, an interesting development around this equation for the deterministic PDE, and so there is a motivation to consider also the stochastic version of it. Okay, so the talk will be divided basically, I would say, in 3 parts, not 4 any. The first one will briefly introduce these Navier-Stokes equations with the Coriolis force. I will explain what the influence of the Coriolis force will imply on the fluid. And then I will introduce the stochastic version of it, stochastic Navier-Stokes-Coriolis equations in 3 dimensions with periodic boundary, with certain boundary conditions. So this is based on joint work with Matthias Hieber from Darmstadt. And the final part of the talk will be about the results in the 2-dimensional case. In the 2-dimensional case, of course, you know, it is easier, and also this is the case in this for this equation. So the picture in 2 dimensions, I think, is quite completed now, and this is partly joined with Abdelhadi Essaïr from Berlin. Okay, so this is the equation I will be talking about. So we're looking at an unbounded layer in of this type, so R2, which is called the horizontal direction, times some finite interval in the vertical direction, and B is the height of the layer in some sense. And we are looking on this state space at the following equation. So this is the usual Navier-Stokes equation. P is the pressure, U is the velocity field of the fluid we would like to interested in. This is the convection term, this is the Laplacian. Nu is the viscosity, and the additional forcing term here is this part, which is just the Coriolis force, which forces the fluid to make some rotation. The axis of rotation is chosen to be the vertical direction, so E3 should be the z coordinate, the third coordinate, and omega here is called the angular velocity. So that describes the velocity of the rotation of the fluid along this vertical axis. As usual, this equation comes with certain conditions. The first one is well known. This is the divergence-free condition. So we are looking at incompressible fluids. So the divergence of U of the velocity field is 0. And then we have boundary conditions on the layer. On the bottom of the layer, so for the vertical component to be 0, we impose Dirichlet boundary conditions on the velocity field. And on the upper bound, on the upper side of the layer, on the top of the layer, so we have a constant velocity. A constant velocity dragging the fluid in one deterministic direction. For simplicity, it is chosen in this way, so the velocity is only in direction of the first, so the x coordinate, and so it comes with a certain scale. The scale is given by this real number UB. And then we look at the initial value problem of this, well, in some sense, stationary Navier-Stokes equation with this additional Coriolis term force. So what you think about is the following. So this is the situation, how you should think about it. So you have actually you want to model this fluid, which you could, for example, think of the ocean with a bounded, so you model this as a bounded layer. B is the top, 0 is the bottom of the layer, and because there is some wind force on the surface of the ocean dragging the fluid in one particular direction, And on the bottom of the sea, the influence, of course, of the wind should be 0, so there should be no, in some sense, motion of the fluid. So that explains the Dirichlet boundary condition. And now the influence of the Coriolis force can be explained as follows. So if you look at the surface of the ocean, and the wind drags, for example, in this direction, and there is a Coriolis force, let's say in this direction, so clockwise rotation, that forces, so the wind drags the fluid in this direction, and the Coriolis force on the same, at the same time, drags the fluid a little bit in this direction. And then you can think of this ocean in the number of several thin layers, and each of the layer which is dragged in this direction drags the layer below it even further in this direction. Of course, the influence decreases with the height, and what comes up is this so-called Ekman spiral. So here you see what I've sketched. So this is the direction of the wind. This is the direction of the fluid due to the Coriolis force. And you think of several layers of the ocean. Below the layer, or in each other layer below it, the fluid is even more directed into another direction. So what comes up is a so-called spiral. So this is what you see actually also in reality, this kind of motion. The depth in reality, the depth of this in reality is approximately 100 meters. And you can even see that the increasing depth of the fluid, of the ocean actually, the direction of the fluid can be even opposite to the wind direction. Okay, so this is the, if you want, so phenomenological description. What is nice of it, you can really solve this or make an analytic description out of it. Namely, these are the so-called Ekman spiral. This is exactly what I described here before, and these are the explicit stationary solutions of the 3D Navier-Stokes with Coriolis force. So you see there is some choice with according to the height. So these k here coming up in this parameter delta in the definition of the spiral, in some sense gives you something like the frequency or the winding number of the spiral. Okay, so this is the phenomenological interest in this equation. So it describes, in some sense, some geophysical phenomena, but there's also some mathematical motivation for it. What you can see is that this equation 1, so this Navier-Stokes with Coriolis force, has a limiting equation if the angular velocity becomes large. So if you rotate the fluid very fast, what you see is that the motion of the fluid stabilizes. And that means for high angular velocity, so if omega is very large, you can decompose the fluid almost into the horizontal directions and the vertical direction. And this gives you better a priori estimates for the solution of the Navier-Stokes with the Coriolis force than you have in the three-dimensional ordinary case. So if there's no angular velocity or the angular velocity is low. And that means, so first of all, you can derive rigorously the limiting equation, which is clear, you can guess it, if you rotate the fluid even faster and faster. But there is also a rigorous mathematical result about that. So for example, for large velocity, one has existence of global strong solutions. This is a result which was first proven in 1999, and it is independent of the size of the velocity field. So it's really a uniform existence of global strong solutions.
So do you mean that if omega becomes big, the
Large.
the spectrum of the linear operator somehow moves far to the right, or
No,
or not?
no, because the energy is conserved, and also the entropy in one dimension, in two dimensions. So that is not the point, because it's a rotation. The rotation doesn't change the spectrum. Well, it changes the spectrum, but not the real particles. Okay, and well, for example, another result in this direction is if the angular velocity is large, existence and uniqueness of global, I forgot this, of global Mahal solutions is known. So this can be found, for example, in textbooks on rotating fluids. But the second result is a little bit weaker. So here, the theorem is in such a way that the bound on the angular velocity depends on the initial data, actually. So in some sense, this is a weaker result than the first one. Okay, so this is the mathematical motivation. And now it's in some sense clear that one should take as working in the area of stochastic partial differential equation, to take interest in this topic and try to, how to say, look at the stochastic analog of this equation. Before I do this, I just recall a recent result concerning stability of this Ekman spiral, which I just mentioned in the deterministic case. So, to make the statement precise, I need to introduce the function spaces. The function spaces will be for V, which is the difference between the velocity field and the stationary solution. And for that, you can impose Dirichlet boundary conditions. Because what you want to study in some sense is how the fluid for large time will approximate the stationary solution. And then you can get rid of these, in some sense, weird boundary conditions. So for the difference, so for the velocity field V, which is U minus the Ekman spiral, we can impose here the Dirichlet boundary conditions at the top and, sorry, at the bottom and the top of the layer. And as usual, then we look at the closure. So this would be the divergence-free vector fields, which are square integrable, and this would be the square integrable vector fields with finite energy. Okay, so this is the result I wanted to refer to. This is concerning the existence of a global weak solution of this fluid U, of this equation. First of all, of course, as in the three-dimensional Navier-Stokes case, there is no uniqueness here in general. Well, there is no uniqueness known in general. If the parameters are chosen in a suitable way, this has to do with the spectrum of this, actually the Stokes operator. Then one can show at least there's at least one global weak solution of this Navier-Stokes-Coriolis equation that converges or decays to equilibrium, or to the stationary solution actually, in L2. So the difference, the vector field V of t converges to 0 as t tends to infinity in this space H. Actually, if lambda is, well, so you even have exponential decay for any lambda less than lambda 0. Of course, if lambda 0 is 0, then you can only have, in some sense, polynomial decay. So the proof is done with not with this Galerkin approximation, but with a Yoshida approximation. And this Yoshida approximation gives you much more information on the decay of the solutions of the Navier-Stokes equation, and actually the Navier-Stokes equations with Coriolis force than the usual Galerkin approximation. So this is the point why they can get more information about this convergence here. Okay. Okay, so this is now the stochastic analog. So this is now, in some sense, natural to look at it. And the first thing to do is, well, if you think of the stochastic Navier-Stokes equation in 3D, the existing results mainly defined on bounded sets because you need some compactness. And fortunately, if you look at the precise analytic description of the Ekman spiral, this Ekman spiral is independent of the horizontal coordinates. It's only dependent on the vertical component. That means you can consider the same stability problem now with respect to, let's say, periodic boundary conditions with respect to the horizontal coordinates. You don't lose, in some sense, the prospective stationary solution. So this is the idea now. And at the same time, you get some compactness, and this is enough for us. Okay, so this is a starting point, and we looked at this particular case. So we look at x1, x2 periodic solutions. So the state space, in some sense, of the fluid will become the two-dimensional torus times this finite open interval. So in some sense, a bounded layer with periodic boundary conditions with respect to the horizontal coordinates. And then we look at the corresponding analog, or first of all, the corresponding function spaces, because we're only interested in differences towards the Ekman spiral. We again impose the Dirichlet boundary conditions with respect to the z, the vertical component or vertical coordinates. And then, of course, we have the divergence-free conditions, of course, as usual, and then we take the corresponding closures as usual. And then just adding some, well, that's the simplest type of stochastic PDE you can think of in this context. We just add some simple Wiener process on H. That need not be, well, the covariance operator need not be the identity. So it's actually it's square root of dWt, where dWt is space-time white noise. Okay. And then how does the corresponding stochastic evolution equation looks like? So we look at the orthogonal projection of the L2 space onto this space of divergence-free square integral vector fields. And if you apply this to the, well, this is not, there's some misprint in the reference here. Of course, if we apply this to this equation 2, not 6, then we end up with the following evolution equation on the space of divergence-free vector field as usual. So dut is equal to nu times the Stokes operator, which is just a projection of the Laplacian onto the horizontal divergence-free vector field. Then we have, well, the projection of the Coriolis force, and this is the projection of the convection term here. And then we, well, this is a little bit cheating here because the Stokes operator is also, of course, subject to the boundary conditions. And I will choose the Dirichlet boundary conditions. Actually, what I mean is I will look actually at the projection of these decomposed equations. So I'm interested in the projection of the equation for this velocity field Vt. Okay, so Vt will be a solution of this equation. So actually this is very similar to what has been shown in the first talk this day by Professor Babu. You just expand in some sense the Navier-Stokes equation, actually here the Navier-Stokes with Coriolis force around the stationary solution here, which is the Ekman spiral in this case. And then you end up with this perturbed stochastic Navier-Stokes equation. The perturbation is given by this expression. Okay. So that's some interest to study this equation for abstract perturbations. So I will formulate the results for abstract, for a general linear operator is B. The only assumption on this perturbation of this stochastic Navier-Stokes is, well, it should be bounded as an operator from V to H, which is the case in our case. It should be linear. Actually, this is not needed, but anyway, so I would like to stick to this because there is no need to consider more general perturbations here in this context. And it should satisfy this coercitivity condition. And well, the most important thing is that omega 0, so the coefficient, the first coefficient, is strictly positive. And WT will be a Wiener process with finite trace covariance. Okay. So that's the usual setting to consider this equation in 3D. The assumptions are made in such a way that this operator actually, and this is actually needed, and this is why I assumed that this is a bounded operator. The perturbation, this perturbation B of the Stokes operator generates an analytic C0 semigroup with this growth condition, which is in some sense useful. Okay, so this is the result concerning the solution in 3D. So, and this is the usual, if you want to be expected result, namely, so if you start, oh sorry, this is completely wrong now. If you start with an initial condition, xi, which is measurable, square integrable, and independent of the driving Wiener process, then there exists a weak martingale solution. Okay, I've written this representing Brownian motion with a tilde here, and this is a different actually probability space to make it clear that this is a weak solution. And you have these energy estimates which are familiar from the unperturbed Navier-Stokes case. So this, in this respect, the result is the same, and the proof also is similar to the unperturbed case. So you can deal with the perturbation B as in the case where B is equal to 0. And we took, for example, the seminal paper by Flandoli and Katarek in PTRF from 1995. They use the construction via Galerkin approximation, tightness, and so on. Unfortunately, the Yoshida approximation doesn't work, since that seems the case. So the additional, how to say, decay properties, which you can, how to say, derive from the Yoshida approximation, unfortunately, they cannot be, how to say, derived in this setting, well, with this approach. Well, and if you apply this in particular to the perturbation which is given by the Ekman spiral, so if you expand, in some sense, the stochastic Navier-Stokes equation with Coriolis force around the stationary solution, then applying this result, you get a weak martingale solution of the stochastic Navier-Stokes equation with Coriolis force. Okay. So, because you have this, how to say, stability in the deterministic case, the result I just mentioned, formulated for the unbounded layer, you can think now around, in the deterministic case, in the stochastic case, of fluctuations around the stationary solution. And you can cover this, or you can formulate this in terms of, let's say, existence of invariant measures for this stochastic PDE, and this is what we did in the next result. So we consider again this perturbed stochastic Navier-Stokes equation. So again, of course, this can be formulated for general linear perturbations. If this assumption is fulfilled, so this dissipativity condition, or if you want, so condition on the real part of the spectrum, of this perturbed Stokes operator, then, so if this is omega tilde, 0 is strictly positive, you can construct a stationary martingale solution of this stochastic Navier-Stokes equation perturbed with this perturbation B. And the invariant distribution satisfies this moment estimates. So this is in some sense not surprising, because you have finite trace on the covariance operator. So for at least for a small epsilon, which is directly related to the coefficients of the problem, this is the operator norm of Q on the space H, you have these finite exponential moments for this invariant measure. And you can think of this measure as the, if you want, so long time or statistics of the solution of the stochastic Navier-Stokes equations around the fluctuations, describing the fluctuations around these Ekman spiral. Okay, so this is so far for the three-dimensional case. And now I will talk a little bit about the two-dimensional case, which is as for the stochastic Navier-Stokes equation, or the Navier-Stokes equation itself, easier. And so this will be now the so-called Navier-Stokes-Coriolis equation on the two-dimensional torus. So what you basically do now is a projection of this model onto a fixed layer, actually. And the corresponding projection, appropriate projection, you have to do it careful, looks like this. So again, you have this Coriolis forcing term. I pretend, well, this is the vector product of the vertical component, of course, with the velocity field, which is only two-dimensional. But if you think of it, so you get actually a projected two-dimensional velocity field. So this is what I mean by this equation. So don't take it literally. And this coefficient now is the angular velocity times this beta times x2. So this comes from this appropriate projection. So that the Coriolis forcing term in the equation looks like this. So we have omega times the, well, if you want, so permutated velocity field times beta times x2, this velocity field. So existence and uniqueness, in the deterministic case, I'm here now, there's no stochastic process so far, are well known. It's not a problem. And, well, we can think about now of the stochastic analog. So we add some noise to this equation, where WT is now a Wiener process on these vector fields on the torus. And so these are now the vector fields of divergence 0 on the two-dimensional torus with mean 0. So this should be the integral over the two-dimensional torus of the velocity field u with respect to the usual uniform distribution for the big measure. Okay. Well, if you apply these, actually in Germany it's called the Helmholtz projection, not the Ray projection, but anyway, it's the same. To this equation, so you end up with so it's a local patriotism. Okay, you end up with this stochastic evolution equation. The noise is a priori chosen already on this divergence-free vector fields, so it's just this result. And so the B now, you should take a quick look at this, becomes independent of this omega. It's only dependent on this second part. So this is because in 2 dimensions, so this is now a particularity of 2 dimensions. In 2 dimensions, every free divergence-free vector fields, so there's a stream function. So every divergence-free vector field can be written as a, let's say, permutated gradient of a function which is called the stream function, which means that which means that this actually will be the gradient of the stream function, and so the projection of this velocity field onto the divergence-free vector fields will be 0. So this is the point, and what remains is only this second part of this vector field. So here's the particularity of 2 dimensions, which is also known for the unperturbed case. So first of all, the conservation of energy is clear. Well, it's not clear, but anyway. So this is also true in 3 dimensions. This is what I want to say. However, in 2 dimensions, we have also an additional invariant, namely the entropy, and this is the infinitesimal version of it. And so that means also this Coriolis force preserves the entropy of the Navier-Stokes with of the resulting equation. Okay, and this will play a role later on. The existence of stationary weak martingale solutions, so we haven't done this, that should be similar to the 3D case. Actually, it should be easier. But okay, so this is not my point here. As probably some of you know, I'm interested not only in this stochastic partial differential equation, but in the, let's say, Cauchy problem of the associated Kolmogorov operator. And this is the object I will be investigating in the subsequent slides. So instead of looking at the mild solutions or martingale solutions of the SPDE, I will look at the corresponding Kolmogorov operator. Here it is. So that's just a generator of the stochastic partial differential equation. So we have the second order part, this trace, infinite trace. Here's the diffusion, the covariance operator of the noise, which is still assumed at the moment to be trace class. And this is the first order perturbation, so where this projected Navier-Stokes-Coriolis equation comes in. So the Kolmogorov operator can be formulated or rigorously defined, for example, on these finitely based smooth test functions. And we would like to solve the Cauchy problem associated with this operator in a suitable function space. And it turns out that a suitable function space is an LP space induced by so-called infinitesimal invariant measures for this operator L. So these are measures which satisfy this condition. So this is the infinitesimal version of the invariance property of a measure with respect to a stochastic evolution equation. If you differentiate it, you get the generator of the SPDE integrated against the invariant measure, and because if the measure would be invariant for the time evolution, the quantity would be constant in time, the derivative must be 0, and so this is the infinitesimal version of that. To make this formally rigorous, you need that, of course, the operator needs to be well defined, so at least this integral should be well defined. Well, before I go to the results for the stochastic Navier-Stokes-Coriolis equation, I would just recall what you get out of these infinitesimal invariants for this Kolmogorov operator. So there is a nice theory around this well, kind of operators, which could be thought of as infinite, as you know, of course, infinite dimensional analogs of diffusion operators. So the Berling-Denis criteria are in some sense the analogs of the maximum principle known for the diffusion operators. So this quantity will be integrated. So if you integrate the function LF against any function psi of f, where psi is increasing, let's say continuous, then this will be non-negative. So that means that this operator will be dissipative on any LP space induced by the infinitesimal invariant measure mu for any p. And then there is a nice criterion concerning the uniqueness of this operator, which is related to the well-posedness of the associated Cauchy problem to this operator in the corresponding LP space. Namely, the closure of this operator in LP, which exists because it is dissipative, generates a strongly continuous semigroup if and only if this well-known range condition is satisfied. So the range of lambda minus L of the domain of these finitely smooth-based test functions is dense in LP. And in that case, so this is a consequence. So in the case of this so-called LP uniqueness, that's a consequence of these Berling-Daigny criteria. The semigroup will be Markovian, so the semigroup generated by the closure will be Markovian, and the stationary Martingale solution will be unique. Okay, in some sense, looking at the uniqueness of the Kolmogorov operator is in some sense the weakest kind of, well, at least the weakest I know, weakest kind of uniqueness you can think of for, in some sense, generators of SPDE, or if you want so, SPDE themselves. Okay, and so the question is, so we don't have, well, uniqueness results for stochastic partial differential equations, nonlinear or semi-linear, let's say, in 3 dimensions are far away. So probably a P uniqueness for the corresponding Kolmogorov operator is an easier problem. Okay, so first of all, in order to make this program run, you need invariant measures. This is, well, in the, we are now in the 2-dimensional case now. If the covariance is of finite trace, you can think of these a priori estimates. So if, first of all, the trace of the covariance is finite in the L2 space of divergence-free vector fields, then you can find already an infinitesimal invariant measure for this Kolmogorov operator having this exponential moment. So this is the analog to the 3-dimensional case. But because we have an additional invariant in 2 dimensions, namely the entropy, we can improve these moment estimates if the trace of the covariance operator Q is also finite in the space of divergence-free vector fields of finite energy. So then in that case, it satisfies even these improved a priori estimates for a small epsilon, of course. So this is a consequence of this second invariant, the invariant of the Navier-Stokes equation with this Coriolis force for the entropy. And that implies now, together with a suitable pointwise gradient estimate on the solution of certain finite dimensional Cauchy problems, the LP uniqueness. So if we have a infinitesimal invariant measure satisfying these stronger exponential moment estimates, then we can show that the corresponding Kolmogorov operator is LP unique in for any P. So not only P equal to 1, but also P equal to 2 and actually any finite P. And the basic ingredient, as I said, is this pointwise gradient estimate, pointwise because it depends on, so it's an exponential of u showing up here. The epsilon can be chosen, so has to be chosen sufficiently small, but as you see, as epsilon approaches 0, we have that this exponential, this factor in front of this square of u becomes sufficiently small. You can integrate it with respect then to the invariant measure, because that has these associated exponential moments, and this is sufficient actually to prove a P uniqueness actually then in any P. Okay, in the case where B is equal to 0, this is a result which has been obtained by Barbu and Prato. Actually, the result now for the general, so for the Navier-Stokes with this Coriolis force is almost analog to this. So this was about smooth noise. Now there is a very interesting thing about this in 2 dimensions for white noise. So if the covariance operator is equal to the identity, which is a very rough noise, as we just learned some minutes ago. But the nice thing is, if you take the identity as the covariance operator, the invariant measures, so some candidates for invariant measures can be explicitly given, and they are Gaussian. So this is an observation which is due to, well, I would say Fursikov already 30 years ago for the Navier-Stokes on the two-dimensional torus, or for the two-dimensional Navier-Stokes. And because the Coriolis force has the same conserved quantities, the infinitesimal invariance of the corresponding Gaussian measures will be true also for the corresponding Navier-Stokes equation with Coriolis force. And the striking thing is that the invariant measure will be invariant of the angular velocity. Okay, so that means, so I just do a little bit rescaling now. So I introduce sigma square in front of the second order part, and the nu is as before the velocity, viscosity. Then you can explicitly show that the Gaussian measure with this covariance operator, so remember AS is the Stokes operator, so I'm always thinking of the operator as negative definite, so minus A is positive definite, has this invariant measure. So this little 2 here, this actually reflects to the case that this will be the H2 norm of the corresponding stream function in 2 dimensions. So this is this little explanation of the this little 2. Okay, in the case where that should be B actually, I'm sorry for that. If there is no Coriolis force, so the usual, in this sense, the usual stochastic Navier-Stokes on the 2-dimensional torus, I could find an integrated gradient estimate on actually, first of all, the finite dimensional Galerkin approximation uniformly in n, integrated with respect to the corresponding Gaussian measure induced by the entropy, which gives you ultimately the uniqueness of the Kolmogorov operator for large viscosity. So this is the result for large viscosity. So nu, the viscosity should be large in comparison to the noise. And then you can find if this is sufficiently large, or you can prove that this operator, this Kolmogorov operator, is closable. Well, it's always closable, but the closure will generate at least in the L1 space induced by the entropy. And you have this, well, once you have the closure it generates, you can think of the resolvent. This is the resolvent of the closure in L1. And this satisfies this integrated gradient estimate. And here you see the effect of the smoothing. So on the right-hand side, we have the derivative, the gradient of the function f in this Sobolev space of order 1 plus alpha. On the left-hand side, we have the derivative of the resolvent applied to this function. And we take its norm in the Sobolev space of order 2 plus alpha. So it's 1 order more than on the right-hand side. So that reflects to the smoothing effect of the Laplacian in this equation. Okay, and it's a safe conjecture. Actually, this is what I did also this week. I checked this, that if the Coriolis term is non-zero, then for at least sufficiently large viscosity, we have the same integrated gradient estimates, which imply, at least so for the finite dimensional approximations, and that imply then the uniqueness of the corresponding Kolmogorov operator in L1. So what is interesting in this is that the invariant measure is independent of these angular velocities, so you can therefore study the limit for large velocity in the same L1 space. So this is a very nice, in some sense, feature and a very nice starting point to look at this. I think this is very promising. Okay, so I will probably, well, okay. I will close with a short remark concerning noise in between. So we had this finite trace noise, this smooth noise, and we had the very rough noise, the white noise. And of course, you know that there are also mild solutions for covariance operators which are not finite trace, but okay, have, let's say, this form. So they, so remember, so recall, so AS is again the Stokes operator, and this is of the order minus 1/2 minus epsilon. Epsilon should be strictly positive, can be small. Then the existence of a stationary weak martingale solution should be similar to the case without Coriolis force. So if the Coriolis force is not there, weak martingale solutions are known. Existence of weak martingale solutions is known. And I want to mention here briefly that the existence proof for the solution of this stochastic Navier-Stokes equation without Coriolis force in this paper by Flandoli-Gattari suggests that the invariant distribution of a solution satisfies these logarithmic moment estimates. Actually, power of logarithm is also possible. And I would just mention that these a priori estimates can be improved to actually these polynomial moment estimates for any power n in this h norm of the velocity and any index gamma less than 1/4 plus epsilon. So this is a corollary in some sense of a general statement concerning improved moment estimates for SPDE of this type. So semilinear SPDE of this type. So we have a good self-adjoint operator of negative type with compact resolvent on some Hilbert space H. We have some semilinear drift term here, and here we have the corresponding stochastic forcing term. And now you can think of a mild solution to this equation. The mild solution can be decomposed always in the stochastic convolution plus the rest. The rest is the solution of a PDE with random coefficient, actually. And these quantities y and w, they refer to this decomposition of the mild solution. And you know the classical quadratic Lyapunov type condition, which says that if this term alpha 3 is equal to 0, then you can get by standard methods the corresponding moment estimates actually of any polynomial type, but also of exponential type. And because of this quadratic term in this convection term of the stochastic Navier-Stokes equation, you cannot get around of this additional third term in this inequality. And the point is that we found actually a method. I think people from dynamical systems, they know it, but anyway, to get around this, to make this coefficient referring to the stochastic convolution in this inequality arbitrarily small by some pathwise control on the stochastic convolution. So this is the message which I want to transport here finally. So that's a little trick which gives you a pathwise control on stochastic convolutions of this type, A minus lambda. Lambda is somehow a damping factor which will be chosen random in the end. And you can actually find a pathwise control on this stochastic convolution of the right-hand type, where the right-hand type depends basically on the modulus of continuity of the one-dimensional independent Brownian motions. Actually, this trick we found in a paper by de Buch in the context of stochastic Burgers equation, but it is very involved and written up in a not user-friendly way. We have now found a general argument. Actually, they didn't use this knowledge about these modulus of continuity of the Brownian motion. They used factorization methods and it was very, involved. But basically, you can get very easily a pathwise controlled stochastic convolution, which means that under appropriate decay of the eigenvalues of the operator, of the self-adjoint operator showing up here in the linear part of the SPDE, you can get a pathwise control of the stochastic convolution in suitable fractional Sobolev spaces related to the to the self-adjoint operator A, which is of this type. So you can write this as lambda to the minus 2 epsilon. If lambda gets large, this becomes small, arbitrarily small, times some random variable which is independent actually of lambda and has finite moments of any order. So this is the trick which works in general and can be applied in particular to these equations with quadratic nonlinearity. So that's all. Thank you for your attention.
You mentioned that sometimes maybe you can get more if you do the Yoshida approximation instead of Galecki approximation. Maybe I missed your further explanation. Can you comment a few words about this?
Well, the Yoshida approximation is an approximation with the help of the Citigroup of the Stokes operator. Since you know the decay properties of the Stokes operator explicitly, you can use these decay estimates in order to derive decay estimates for the ultimate limiting equation. That's the point. You could, in principle, think of a more refined Galerkin approximation in the same way, but it's more difficult.
Any other question?
You mentioned this two-dimensional case with the cylindrical nodes. So were you able to do this proof counterpart of the result by de Buch and Purgain for the existence of solutions with such irregular noise?
Well, no. So not on the path, not on the on this. So that's what I say. The Kolmogorov operator is a more general object. So it does not use all this, the whole structure. So the result, the existence of a Cauchy problem is a weaker statement than solution of the whatever kind of solution of the SPDE. And in some sense, you can use now, of course, these gradient estimates in order to construct processes, because you have a lot of information about the corresponding potential theory now at hand. But this is not what I'm doing. But probably I would like to refer. So this is, I think, the measure. There's a lot of criticism with this measure.
No, I was not criticizing.
No. I want to complement your question or my remark to this. There's a lot of criticism to this measure. Why? Because it leaves the Fourier modes independent. So the Fourier modes with respect to these measures are independent, and this is what is not believed. It is quantity. So in some sense, looking at this Cauchy problem with respect to this invariant measure gives, in some sense, a positive or negative hint whether this is a decent invariant measure or not. And in some sense, this says for large viscosity, the Gaussian measure with respect to the entropy is a decent invariant measure. So this is a strong hint for this. Otherwise, you wouldn't have uniqueness here.
So I guess there won't be a mild solution in that case, right? In the case
Yes.
that you have, that
Yes.
you have white noise.
There's a work by Flanduli and I think Gotzi on a certain regularized mild solution, but no, I think you are right. There will be no mild solution to this.
But there's no proof, but
No, there's no proof, no. But I think you are right.
If not, let's thank Wilhelm.
So, as I'm the last speaker of this workshop, so it's my duty now, or it's my pleasure. Sorry. Sorry. No, it's my pleasure to thank the organizers for this workshop. So it was, I think, a successful workshop, and the organization was excellent. So would like to give a and I would also like to thank the staff of this Newton Institute, which in some sense made the I think so, I don't know, but anyway I know it from the, let's say, the communication with the staff here. So they organized very well, and it shows up that they are really professional, as the director said it on the Monday on the opening of the workshop. And last but not least, I would like to thank all organizers actually of this program on stochastic partial differential equation. So since this is the opening workshop, I think there will be an interesting program coming ahead in the next months. So I would like to give a hand also for that.